Good day, I'm Norman Wahlberger. In today's video, we are going to move towards understanding abstract algebra, a large and lovely area of mathematics with lots of applications, especially 20th century developments. And we're going to look at laying the foundations for this subject in, of course, a better and more solid and more tangible and computable way than we currently have. And we're going to be relying very much on our data structure point of view and the lessons that we have learned about just how to set up fundamental arithmetic and a little bit of Maxwell's and Bexel's. Okay, so what is abstract algebra? Well, it's not that easy to say. It's a kind of an extension of arithmetic or algebra to more general situations. And these general situations include lots of things which have perhaps some fancy names. So we're talking about groups, rings, fields, vector spaces, algebras, lattices, modules, Lie algebras, hypergroups, and one could fill the page with more objects that are studied in modern abstract algebra. Roughly speaking, this list sort of corresponds to the order in which an undergraduate might learn about these various topics. But there's quite a bit of variability possible. Okay, so the common features of most of these situations is that we have some basic algebraic objects, usually one or two algebraic objects, and they're often called addition or multiplication or variants of them, but not always. Another common feature is that we're generally generalizing common or familiar objects or arithmetical situations. So the idea is that we have some particular domain of investigation in which we have some arithmetical operations, and we look at the essential features of that situation and try to extract the sort of skeletal underpinnings of that situation in order to generalize. So we start with a particular object and then we want to generalize to include a wider family of objects which shares a lot of the properties of the main one that we started with. And the idea is then to, try to say things in a way that covers this wider range of objects, even though maybe we're still focusing our intuition on the fundamental examples. Okay, so what do we do in abstract algebra? Well, one of the kind of things that we do is we're interested in structure. We're interested in determining what these objects look like. And we're interested in classifying them to create lists or sort of a taxonomy of various things that satisfy the framework that we have generalized. And once we start doing abstract algebra quite a lot, we start to see that there are certain patterns of thinking, certain standard kinds of constructions or ideas that end up recurring, including, for example, the idea of substructure. We identify some particular kind of structure, and then we look inside those structures for other structures which are basically similar to the original one. We think about product or sum structures. We've got some kind of object, maybe a group, and over here's another group. We think about how we can combine those groups, maybe add them or multiply them to create some bigger group. We look at quotient structures. That's a little bit more subtle. So that's what happens when you have one object of a certain kind, and then inside you have some other kind of object, but the same kind, but it's definitely inside. And then the idea of sort of taking a quotient, like dividing the big one by the little one to get a third kind of object of the same kind. So investigating when that's possible, that's an interesting kind of question. A very general kind of consideration is the idea of understanding relationships between two objects. Like let's say we're looking at lattices. So here's a lattice, and there's a lattice. We're interested in what kind of relations there are between these lattices. And this is often framed in terms of word homomorphism, which we think of as a mapping or a function or a transformation that takes the elements of one lattice to the other lattice, but preserves the lattice properties. So whatever a lattice is has certain properties, and we want our relations and homomorphisms to preserve or to respect the various arithmetical or algebraic structures that we have. So these are some of the common features that figure in pretty well the study of any one of these kinds of abstract algebraic structures. So today we want to give a very brief kind of overview to some of these kinds of objects in a kind of cursory overview, but with a traditional point of view. All right, so this is following sort of standard thinking, and then later on we want to move towards a better, new, improved way of thinking about these same things. But let's start with a somewhat more familiar look at them. Now, it's often considered that group theory is the natural entrance to abstract algebra because it's an algebraic situation where you only have one operation. And the operation is sometimes called addition and sometimes called multiplication. So I'm not going to, in this lecture, concentrate on the official definitions of things. I'm going to rather give you a brief orientation by showing you some examples. Now, we actually have talked about groups a number of times already in this series. You can have a look through the series for some examples. For example, when we were talking about projective line, projective plane, and isometries of, say, the projective line. Okay, so another example of a group that we've talked about is these U groups. So, for example, U10. And U10 was the integers less than 10, which are relatively prime to 10. In other words, which don't have any factors in common with 10. So that would be 1, 3, 7, and 9. And we saw that we could make a algebraic structure out of just those four objects by doing multiplication mod 10. All right. So here's the multiplication table that we considered. 1 is the identity, so 1 times anything is that anything. And say 3 times 7, ordinarily that's 21, but if we're working mod 10, 21 is the same as 1, so 3 times 7 is 1. And this is a commutative group reflected in the symmetry of the multiplication table, that the 9 times 3 entry is the same as the 3 times 9 entry, so that entry and that entry are the same. And that's a very special and pleasant kind of group. It's much simpler than the non-commutative groups. And so the basic properties of a group is that the multiplication should be associative, that there should be an identity element, in this case 1, and that every element should have an inverse. Which basically means that along every row or every column you can find a 1 entry. So those are commutative groups, and they are quite a pleasant thing to study, and they come up in practice, for example, here, okay, but in other situations too. And then there are non-commutative groups, which have the same underlying rules, except that the multiplication of two elements doesn't need to be commutative. So A times B does not have to be equal to B times A. And we've seen some examples of that. For example, the group S3, which is the group of permutations of three things. We can label those by thinking about the ordered sets, which have 1, 2, and 3 as their elements. So these are like ordered sets or permutations. These are the 6 possible ways of rearranging 3 objects. And one interpretation of this group S3, it's the symmetric group on 3 things, is as the transformations of a triangle. So if we here have a triangle with positions 1, 2, and 3, then for example we can think about the transformation that takes this triangle and rotates it by a third of a turn in this direction. Okay, so we'll take this triangle here to this position here. Let's call that transformation sigma. Okay, then that transformation can be recorded. One way is to say, well, the one object goes to the 2 position. The 2 object goes to the 3 position, and the 3 object goes to the 1 position. And we could record that by having a little table like this. Here are the initial objects, and here are the new positions that they go to. So the object 1 goes to the position 2, the object 2 goes to the position 3, the object 3 goes to the position 1. And once we have a little table like that, we can also say, well, why don't we just record the last row, the bottom row, because the first row is always 1, 2, 3, and so we can associate to this thing the ordered set 2, 3, 1. So that would be one way of identifying these permutations or transformations of a triangle with these ordered sets. And in this context, the multiplication is that of combining or composing transformations. So you do one transformation and then you do another transformation after that one, and that's called composing the transformations. And that gives an algebraic structure to our permutations. That's a non-commutative group. So that's a very interesting family of algebraic objects, very beautiful, very rich theory. The non-commutative situation being typically a lot more advanced and richer and more complicated than the commutative theory. This division between commutative and non-commutative kinds of abstract algebra is a central one in the subject in terms of organizing the subject. And that also holds with our next example, the example of rings. Okay, so let's start with an example of a commutative ring. And there's a very familiar example, the example of integers, or int. So now we have 2 operations, addition and multiplication, and it's a question of studying not just those operations in themselves, but also how they interact. So for example, the addition operation is commutative and associative, and also the multiplication is commutative and associative. It's the multiplication being commutative that makes the ring being called commutative. The addition always has to be commutative. Now in addition, the 2 operations interact via the distributive law. That's very familiar to us. And there's also some extra kinds of things. There's a 0 element, which plays an identity element in terms of addition. There's a 1 element which plays an identity role in terms of multiplication. And then there's a notion of inverse, closely related to the -1 object, that allows us to start with an element 6 and obtain the inverse of 6, namely such that when we add them we get the additive identity. So that's an example of a commutative ring. And generally, we like to have more than one example of an algebraic structure. If we don't have more than one example, then it's not really important enough to think about generalizing. So we want to have something where we have a couple of different situations that all have some common features, and we can say, there's some common things going on here in these different situations. Let's abstract those common features and study this thing abstractly. Okay, so aside from the integers, another important commutative ring is the ring of polynomials, or for us, polynumbers, which we might denote by polyint. Okay, so we're talking about things that look like this in the polynumber language. So we have combinations of numbers, alphas, alpha squareds, alpha cubes, and so on. These are familiar ways of writing things down, which actually officially are more like column vectors. And we know that we can add to such polynomials or polynumbers, basically pointwise. So 2 and 3 give us 5, the alpha minus 4 alpha give us minus 3 alpha, and the alpha squared was there. But we can also multiply them in the kind of distributed way, so that 2 minus alpha times 1 plus 4 alpha would be 2, and then plus 8 alpha minus alpha is a total of 7 alpha, and minus 4 alpha squared. And with these 2 operations of addition and multiplication, we get a situation which is very parallel to that of the integers. It's a little bit bigger and more broader, but it shares a lot of essential features. And so you can think about a commutative ring as being some kind of attempt at generalizing what goes on in these 2 examples. So after commutative rings, there's some case to be made that a field is a natural then next kind of abstract algebraic object to consider. So the main example there is the rational numbers. Okay, and that's a algebraic domain where we have addition and multiplication, but prominently we also have the inverses of those. We have subtraction, which we also have in a commutative ring, but what's especially important is that we have division, at least almost all the time. So a field is a commutative ring with, in addition, the possibility of division by non-zero numbers. So we want that every non-zero number has an inverse, a multiplicative inverse, just corresponding to the fact that if you take a rational number like 5/7, then its inverse is 7/5. So the rational numbers are a very interesting and important algebraic domain, but also full of some subtlety. In particular, there's the key ambiguity and specification of rational numbers, because we know that rational numbers are not uniquely defined. 2/3 is the same as 8/12, same as -14 over -21. And the rule, of course, is that there's an unambiguous way of deciding whether two things are equal. So we would check this by checking that 2 times 12 is the same as 3 times 8. Okay, but that does make the analysis and study of rational numbers definitely a little bit trickier, because you have to factor in this ambiguity in how you specify one of the objects. And then, for example, we have addition in a kind of a familiar way that we all know. We have multiplication, which is familiar enough. We have division, where you basically multiply by the inverse, or this reciprocal. And so these are standard examples, but it's a very rich field, a very important field. Now, students of abstract algebra these days learn immediately that there are then other fields as well. There are fields like the real numbers and the complex numbers, and maybe fields like a plus b root 2, where a and b are rational numbers. This is highly unfortunate. Okay, it's highly unfortunate when students of abstract algebra, after having spent some time thinking about rational numbers, are quickly indoctrinated to believe that there's then these other fields, R and C, that are pretty well the same as rational numbers. Okay, this is a huge misunderstanding and a blind spot in modern mathematics. Okay, so in fact, going from rational numbers to R and C is a huge step in complexity that really takes us outside of abstract algebra. Okay? The essence of the idea of these two things, which is already faulty, but the essence of this faulty idea is that we can start doing arithmetic with infinite processes. Okay? That's the whole point, that we can take an infinite number of additions, we can take an infinite number of multiplications, and we can output the results of those infinite kind of procedures and have a viable arithmetic. But modern students are not told the subtleties, and so they're just taught that, well, there's the rational numbers and there's the real numbers and the complex numbers, and they're all pretty well the same. But the reality is that they're dramatically different. This is much, much more solid. These things are fraught with difficulties, and in fact, when you look carefully, they don't really work. Okay, so we have a very big difference of opinion when it comes to field theory, and that's going to be a big point here, that our field theory is going to be very different from the field theory that you learn at universities these days. We're going to do field theory solidly, correctly. So then there's non-commutative rings. So we started with commutative rings and then fields, and now we can sort of backtrack to non-commutative rings, where the addition is still commutative, but the multiplication now is no longer commutative. Okay, there's a standard example of this, which is a very rich example and hugely important in mathematics, the example of matrices. And the simple example is already very interesting, the 2x2 matrices with integer entries. This is an arithmetical domain in which we have operations of addition and multiplication. So the addition of 2x2 matrices is just the usual pointwise one, and the product of 2x2 matrices, we know, it's this sort of funny multiplication where you, to get this 2, you multiply that row by that column. So 1 times 2 plus 2 times 0. And this minus 1 is 1 times minus 7 plus 2 times 3. And that minus 2 is minus 1 times 2 plus 4 times 0. And that 19 is minus 1 times minus 7 plus 4 times 3. And in this arena, we also have this distinguished 0 element, which is the identity for addition, just the matrix of all zeros. And then we have this curious identity element for multiplication called I, which is this matrix with 1s on the diagonal and 0s off the diagonal. Okay, and this whole story generalizes to 3 by 3 matrices, 4 by 4 matrices, and so on. And so we have this family of these non-commutative rings were very important in mathematics, generating all kinds of interesting arithmetic that goes beyond the arithmetic that we're familiar with. And the last abstract algebraic structure that I want to tell you about today is probably the most common one, the one that undergraduates end up using practically the most. The idea of a vector space over a field. Okay, there's a very common example of this, which is the vectors in dimension 3, say, with rational number entries. So this abstract object is actually rather technically subtle to set up, because you need to understand what a field is first. And we're going to talk about this. Let's say if we use the rational numbers, which is our generic field, then we can think about vectors with 3 components whose entries are rational numbers. Okay, and the operations here, there's 2 operations, but they're not exactly what you might think. The first one is vector addition, which is just the usual addition of vectors component-wise, like here. But the multiplication is a more limited multiplication. It's not really the same as in the ring story. It's not as if we multiply 2 vectors. Rather, the multiplication here is what's called scalar multiplication. So in a vector space, we have the idea of multiplying vectors by elements in our field. All right, so for example, here is a vector, and here is a number 5, which we think of as being an element in the field. And 5 times this vector, that makes sense, and it's just the obvious point-wise multiplication of each entry here by that scalar. And this is a very important algebraic object because it's the algebraic embodiment of our 3-dimensional space, right? We live in a 3-dimensional space, and we like to describe that by having coordinates in a familiar kind of way, and then labeling axes, and then using parallel lines and so on to specify directions. So for example, we go 2 in this direction, and 3 in this direction, and 4 in this direction, then we can get this combined transformation from 0 up to here. So this red directed segment is the vector 2, 3, 4. So it gives us a very physical interpretation of this algebraic structure, and this is hugely important in engineering and many applications, and really is a workhorse for linear algebra, for setting up linear algebra. There's other examples of vector spaces over fields. So for example, we could take the 2 by 2 matrices. In fact, we could take n by m matrices. It doesn't have to be square. So just the space of matrices of a fixed kind, or a fixed shape, with rational number entries. You can add those, and you can multiply them by scalars, and so that naturally forms a vector space. But there are in fact lots of different examples of vector spaces, and this is a kind of a key abstract algebraic object that we're in fact going to start with. So when we start looking at abstract algebra, this is actually going to be the first one that we look at sort of seriously, and that'll be quite interesting. But before we do that, I want to share with you some of the challenges that modern abstract algebra has. Now, abstract algebra is not as fraught with difficulties as modern analysis. Modern analysis has very, very serious problems. The problems with abstract algebra are also not to be diminished. They are also reasonably serious, but they're not as extensive as for analysis. But nevertheless, we do have to acknowledge what they are and have some understanding of the challenges that we need to overcome to set up abstract algebra properly, solidly in the 21st century. And so the first thing to understand there is what the problems are, and then we can talk about how we're going to overcome them and move beyond. All right, so that's what we're going to do in our next video. We're going to look at some of the logical challenges with modern abstract algebra. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.